Hey everyone, welcome to our continuation of the Advanced SQL course. So looking outside, currently it's really lousy weather outside, so I thought it would be time for a new backdrop here. I have relocated myself into the Millennium Falcon. Okay, so in the last video we've concluded our discussion of arrays. This doesn't mean that they won't pop up now and then. They even pop up in this video, although the topic and the focus of this video is shifting slightly. We are talking about table generating functions. Okay, and one entry into this topic would be a closer look at the unnest function, that we've used to bridge from arrays to the world of tables. Unnest would pick the individual elements of an array and return them as rows over which we can iterate. And one question you might ask yourself is, what's the type then? What's the type of unnest? It's one of these set returning functions, as we call them. And these are special and very useful in SQL, and they deserve a special discussion. Okay, so this bridge between arrays and SQL worked because we were feeding arrays of a particular element type tau here, okay, and we were getting something that a SQL query can iterate over, and that's just a bag of rows, actually something that is very similar to a table. That's what you can see here actually. This is the type that PostgreSQL assigns to the result of unnest. It's a set of tau. So if the original array stored some taus, some integers, some booleans, some rows of something, then unnest will leave us with a set of these integers or booleans or rows or something. Okay, and this is something that a SQL query can iterate over. Okay, so these taus are viewed as rows over which we can iterate, and we could just use the regular SQL constructs to iterate and to consume the result of unnest. Again, there's a bit of unfortunate naming going on here. So set of tau is an okay name, but maybe bag of tau or table of tau would have been a better name, because this is actually what we are getting. We're getting something that can act like a table. The result of unnest can act like a table, and we can iterate over it. We can bind row variables to the result of this function, and it just acts like a table. So maybe these would have been better names, but I can live with set of, that's fine. There is another name going around for these set returning functions, and it's also quite fitting, I would say. It's the table generating functions, or the table functions for short. And that really makes sense. We can use these functions in the places where we would otherwise expect a table in a query, namely in the from clause, where we can then bind row variables and start to iterate. All right, several of these set returning or table generating functions are already built into any SQL dialect of any database system that you are going to use. Several are built into PostgreSQL, and we will have a look at view of them, at a selection of them, so you get the impression of what's going on there. But we could also define our own set returning function. That's really a powerful thing. Here and there, this might pop up in the rest of the course. Okay. We have actually met some of these set returning or table generating functions already. Of course, we have just discussed unnest. But there has been another function that we have been using to good measure to generate the contents of tables, for example, and that's the generate series function. Okay, the generate series function also constructs a table that we can then iterate over. It constructs this table not from an array, but from these from and to values, to the beginning and the ending of an interval of values, which we will then enumerate, which we will walk this interval from up to 2. We will never exceed the 2 value, the t value here. And the strides that we are taking, the steps we are taking, have a width of s, which by default would be 1. Okay, so evaluating this particular generate series function would leave us with a row that contains an f value. The next row would contain f plus 1 times s. The next row would contain f plus 2 times s, and so on, until we hit something that's f plus n times s, which would be the last value. As soon as we reach t or would exceed t, we never actually exceed t. This is made sure by generate series, then this enumeration would end. All right. It's obvious that the f and t and s values have to be of appropriate type so that we can form this type of arithmetic here. Of course, any number type would make sense here. So f and t and s might be number types, but f and t might also be timestamps, and s might be intervals that we are using to walk between these two timestamps. Okay, so that would be generate series. Generate subscripts again has a relation to arrays. We would feed an array xs into generate subscripts and then specify one particular dimension d in the array. Often this is the first dimension when our arrays are just flat, but they might be multidimensional, then d might be larger than 1. So if we have decided for a particular dimension, generate subscripts will generate all the subscript, all the valid integer subscript that we can use to index into array xs in this particular dimension. So if in dimension d xs has indeed n elements, then generate subscripts would generate these n subscripts for us. We could iterate over these, take each of these individually, and then probably use these to perform lookups into xs itself and to process the array elements of xs in some appropriate fashion. Okay, so this could also be a very helpful function when we try to perform the step from the array world into the relational world, into the tabular world. Okay, so let's quickly switch over to the editor here, and well, we have seen generate series in action already. So I brought only very brief and very simple examples. So that would be one example of generate series that, as you can see, I'm using it here in the place where I would normally use a relational table. All right. And the semantics of generate series dictate that we will see a number sequence that starts with 1 and then proceeds in steps with 2. Okay, so we would probably see 1, 3, 5, 7, 9, and we won't see 11 because we will never exceed the upper bound specified here. So let's see whether this works. Looks okay to me. The odd numbers from 1 below 10, including 10, but okay. So well, we could also iterate or generate a table from the numbers in the interval between 0 and -2. Of course, to reach this upper limit, we would have to have a negative step width, and that's possible too. So let's see what's getting out of this. Okay, so we start with 0 and then move our way down until we hit the upper limit -2.0. All of this can be done with generate series. Okay, so how about generate subscripts? To play with generate subscripts, we need an array. Okay, we need an array for which we can generate valid integer indices. Okay, so let's bring an array into play, and you see how I'm generating this particular array here. I'm using a string as input to the string to array function. That's a built-in function that will convert a string into an array. And how are the array elements determined? Well, the string is being broken into pieces at this particular separator character. Okay, breaking this particular input string at the separator character will leave us with 2 elements, with a star and the vors element. Okay, so that's the array xs that we are extracting here. We are iterating over this literal table. It will only contain one array. Okay, and the array will be named xs. It's the only field that this row contains. xs is our array. We are looking into its first dimension. This array has 2 text contents, one string star, the other is vors. That's what we are probably going to see. I will iterate over the valid integer, indices 1 and 2 in this case. We will index into the string, into the array, I'm sorry, and we will see star and wars here. More subscripts would have to be generated if the array has more elements, and we could easily simulate that. We could, for example, indicate to the string to array function that we are interested in splitting the string after every character. So this would be one array element and this would be one array element. All of these would be individual array elements. Let's split after these. This will lead to a longer array that has more valid subscripts, and this is what we are going to see in the output. Okay. There's other set returning functions or table generating functions that we haven't seen. And let's have a look at two of them. They are related to regular expression matching in PostgreSQL. All right. So both functions will use as input a text T, a text string T, and then look inside text string T. We'll try to find matches in T regarding a given regular expression RE. RE is a regular expression that looks like the regular expression that you know from your favorite regular expression library that are available for any programming language. Okay, so there's a regex matches set returning function that will yield a set of, or a table of text arrays. Okay, so a table of text arrays is returned from the regex matches function. And you can see what's being done here. We would use this regular expression to find all matches because of this parameter G here, the global regular expression search. So we would try to find all matches of the regular expression inside the text T. There might be many of such matches. Each of such a match will lead to a row in this particular return table. Okay, so each match would be one row. Inside this row, we would find a text array. And the text array holds the matches of the so-called capture groups that are being filled when we find a regular expression match. Capture groups, that's a notion that stems from the world of regular expressions or modern regular expressions, where parts of a match, particular substrings of a match, can be identified and then extracted individually. Okay, so we will see an example on the next slide and also in the editor. So any match might have many of such capture groups. The example that we will see on the next slide has 3 capture groups in each match. So we would obtain an array of matches, and inside of these matches we would have an array of 3 capture groups. So quite a complex result that is going to be returned from regex matches, but this is a complex type or complex collection type that is able to cover that. Okay, regex split to table is somewhat easier. We would use this regular expression as a separator regular expression to find its occurrences inside text T. Wherever this particular regular expression occurs, text T will be split up into separate pieces. And all of these individual pieces are being returned to us in this as individual rows that we can then iterate over. So that's a typical use of a set returning function. In this case, each of the split pieces makes up one row. It's a set of text that is going to be returned. So if we find n matches for a regular expression, the string will be split into n plus 1 pieces. So let's see at an example. Let's look at an example rather. So this would be an example of regex matches. So we are looking for the actual matches, for all of the actual matches that we can find in inside the string. And once we have found the match, we will look at at capture groups inside the match. So let's see. The input string that we have here is some chemical formula. Okay, all right. So we try to separate this chemical formula in the individual components, in the individual atoms that contribute to this element. Okay, and this is the regular expression that will do this for us. This regular expression will parse this chemical formula and separate it into individual atoms. You see that some atoms come with atom counts, like this C6 here. Some of these atoms come with charge indicators, with charge numbers, like it's 3- here. So 073-, this makes up one match. This makes up one match. It has the name of the element here, of the atom. It has the atom count, and it has the charge. And these are the three individual pieces inside the match that are of interest to us. We would like to separate these and have them extracted individually. And that's where the capture groups come into play. So as you can see, let me put the light on here and make this more specific. You see that there are parentheses inside this regular expression, and these make up one capture group. Okay, so this would be the capture group that is tasked with extracting the atom name. So that would be just a sequence of alphabetic characters. The second capture group would be tasked with extracting the atom count. So that would be a sequence of subscripted integers here, between 0 and 9 subscripts. And this capture group, the last capture group between these parentheses, would be tasked with extracting the charge. Okay, the charge might be followed by such an optional plus or minus superscript symbol. All right. So inside each of these matches, this would make a complete match, and I hope that the citrate element that I've, the formula that I have here, that would match against this particular regular expression. If it matches, we will be able to extract the individual capture groups using the array that is returned for this particular match. The first capture group, the second and the third capture group would be represented in this first, second, and third array element that is returned for the match. Okay, so and that's exactly what's happening here. This is one string. It would probably generate 3 matches for the C, for the H, for the O atom. So we expect 3 matches here, and inside each match we have 3 capture groups. And as you can see, indeed, the return table has 3 entries. So regex matches is indeed a set returning function. We could iterate over the matches using the regular select from syntax here. And in each of these matches, this is an array of text. In each of these, we can identify the capture groups, extract them separately, and prepare them to return a table that we can then use to process the details of this particular chemical formula. So it's a quite sophisticated chemical formula parser. Okay. So I brought this with me in the editor. So indeed, this is citrate. I recalled correctly. Okay. Okay. So this is just the query from the slide. So let's run it. And indeed, we see what we have seen on the slide. It's 3 matches. Some of the matches have no charges. The capture group for this particular piece of the match is empty. And indeed, as you can see, the last capture group here, the capture group 3 for the charge, is indeed optional. And the optionality will not hinder the match. The match will still be there, but the contents of the capture group will be empty, and this is represented by a null value here in the returned result. Okay. We could actually modify this behavior and change the regular expression slightly. As you can see, this is just the same regular expression with the same input. Everything is the same, but this regular expression here internally has changed a bit. Using this prefix modifier for the regular expression will lead us to an empty match, an empty string match, in case there is no charge indicator present in the atom specification. So instead of a null value, this regular expression would give us an empty string. Let's see whether this is the case. Yeah, indeed, there are some null values here, but empty strings that we cannot see in the output. But This is not related to regex matches or the fact that this is a set returning function. This is just the intricacies of regular expression matching. These are not so much in focus here, but as you can see, PostgreSQL comes with a really complete and quite sophisticated regular expression matching library that now and then will be useful when we process textual inputs. Okay, so here's another use of the regex split to table. So a function that we can use to split the contents of a string into individual parts, and what is considered a part is defined by this regular expression. So this regular expression looks for white space characters, any non-empty sequence of white space characters, and indeed there are many such sequences, and you can imagine that this will split the string into Luke, I am your father. Okay, so in a into a 5-row table that we can then iterate over with just the normal select from syntax. Okay, nice. There's variations of splitting strings into individual pieces. We have seen these already. We could use the string to array function again and split after each character. We have seen that before. What we would get here is an array that we could then unnest, and if we even add the ordinality information, we would obtain a character by character analysis with positional information of how the input string looked like. And this tabular representation of the innards of a string will sometimes prove useful when we support or when we implement parsing-like functionality in our queries. There's one particular interesting way to process the output of such set returning functions, and the functional programmers would call that zipping. So set returning functions emit columns of values, normally single column tables for us further to process. If there are many of these functions and they emit tables of values or rows of values which are actually related to each other, so the first rows returned by these functions are related, the second, the third, the nth row are related to each other, then there is a particular modifier or syntax in PostgreSQL which is specific to PostgreSQL. You won't find that in other database systems, which is the rows from syntax. And rows from takes several parameters, up to k parameters, some integer number of parameters here, and each of these parameters would be set returning functions. Rows from would evaluate these set returning functions. These would yield, of course, tables of results. So if k is 2 and we just insert 2 set returning functions in such a rows from call, then we would obtain the result, the tabular result of f1 and the tabular result of f2. Rows from would glue these results together, would zip these results together by row position. Okay, so the first elements, the first results of these set returning functions would be glued together to form a row. And the second and the nth would be glued together to form a row together. If there is any contributor to the zipping that has excess elements like this y subscript n plus 1, that would also be integrated into the zipped result, into the rows from result, but it would be paired with null if other set returning functions cannot contribute an element at index n plus 1. So this is really a positional join, if you will, a positional join of the outputs of the set returning functions. This can be quite useful if you have to incorporate the results of functions that have been individually evaluated but are related by position. We have seen something similar already when we were talking about the unnest array function that can indeed unnest many arrays at once and will then positionally align all the extracted elements to form rows with k. So rows from is a generalization of this same idea the generalization that is applicable to any set returning function here. Okay, so I think I brought an example with me for this as well. Yeah, okay. So this would be an example of the zipping behavior of the unless function, and we have seen that before. So these would be two individual arrays, and one array of the titles of all the Skywalker Saga films, and one array of the episode numbers. And you see that the episode numbers are in a peculiar, strange order here, in the so-called machete order, which is the order in which some people suggest you should watch the films. All right, so episode 4 comes first, 5 comes second, and then the Phantom Menace, and that's exactly the order in the episode numbers, and that's the order too here in the film titles, and they belong together, and unnesting these and then zipping the two together, 4 A New Hope, 5 The Empire Strikes Back, and so on, really makes sense. This is what's happening in this unnest call. It will generate rows with two fields, episode number and film title. And since we add this with ordinality modifier, we will even get rows of 3 columns, in which the last column called watch here will just simply number the entries that we've seen here from 1 to n9 in this particular case. All right. So let's see if we order this output by this particular number. We will see that this is just the order in which the machete order will suggest to watch these films. All right. So this has been generated by the with ordinality, okay, and it's just the numbers 1 to 9. This is a very nice ordering criterion, but unaffected by this, the machete order suggests that we first watch episode 4, then 5, and then 1. All right. Okay. One final example that is related to parsing in a sense. So imagine that you are tasked with the analysis or the syntactic analysis of arithmetic expressions. This would be the textual representation of such an arithmetic expression. It consists of literals, as you can see here, 4 and 10. All right, let me mark this, 4 and 10, and also variables. And all of these are separated by operator symbols, like this plus and this multiplication sign. Okay, so this is admittedly very simple syntax for expressions, and we will build more sophisticated parsers later on. But because the syntax is so super simple, we could just use regular expressions to separate this expression into its literals, into the arguments, and into the operators that make up such an expression, into the plus and the multiplication sign, for example. All the operators that our expression language supports are identified and defined by this regular expression here. It's just the class of, or the set of characters, multiplication sign, plus sign, the minus sign, which has to be escaped here so that it doesn't define a character range, and the division symbol. Okay, so these are the possible operators, and the multiplication sign and the plus sign, they appear among these. They should be identified as operators. Okay, so now let's divide the expression. Let's divide the expression into the literals and variables, so into the operands and into the operators. Once we have these separated, we could then further perform processing, simplification, outputting, whatever you like. Okay, so we would do this in 2 steps. We would first split the expression and the operator symbols. And if we split at these operator symbols, what we get as individual pieces are the literals and the variable symbols. And this is what is being done by the regex split to table. We would split the expression at the operators. And in this case, what we would expect is a table of 3 entries, 4, 10, and x. Second step, we would use the same regular expression and of course the same input expression. and find all occurrences. Find all occurrences of operator symbols inside this expression. So we would of course find two matches, the multiplication sign and the plus sign. Okay, and this would just lastly yield a 3-row table. This, in this particular example, will yield a 2-row table. We would zip them together using the rows from, which will pair the first variable symbol with the first operator it's followed by. The second operand would be followed by the operator it is followed by. The third operand would be followed by the operator, if there is any, it would be followed by. Otherwise, rows from will generate a null for us here. So we should really have information about all the operands and the operator they are followed by. And that would already be a quite useful input for further analysis or for a further manipulation of this input. So let's see, the rows from will sync up the operands with their operators. Okay, this will yield a 2-field or 2-column rows. Okay, expressions first and operators second. Okay, and then we would just output this. So let's see. Okay, so 4 is followed by times by the multiplication sign, 10 is followed by plus, x is followed by nothing. All right. Okay. This is quite a detailed analysis of the input expression already. It's so detailed indeed that we could just reassemble the original expression for that again. We would just need to make sure that we have some information about the order in which sub-expressions operators occurred in the original expression. This has been the first sub-expression or operand and operator pair. This has been the second, and so on. But that's easily added. As you can already imagine, we would just use with ordinality here and add some position information. All right, once we have that position information, we could just feed it into this string aggregate. This is used for aggregation because from all the pieces that we have extracted from all the rows that have separated the operands and the operators, we would like to construct one value, the string value. So that's a task for an aggregation expression. Inside the strings, the operands, the literals or the variables, would come first. They would be followed by the operator symbol if it's not null. If the operator symbol is null, well, let's then just add the empty string to this to the resulting string. And as you can see, I'm using the coalesce function, which encodes or which represents just this particular conditional expression evaluation. If this operator is not null, this operator would be the result of the coalesce call. If this operator is null, then coalesce would return whatever we put here, in this case the empty string. So this is just really a check whether this first argument is null. If it is, then the result is the second argument of the coalesce function. All right. So we would just concatenate these two together. This is string concatenation. All right. All of these operand operator pairs would be concatenated together by the string aggregate function using no intervening symbol whatsoever. And we would make sure that we do this in the order prescribed by the pos column, which is the ordinality information. The ordinality information which would be 1 here, 2 here, and 3 in this particular row. Okay, so we will reconstruct the expression in the original order, intended order. So let's see. Okay, so there we go. This is, of course, the original expression reconstructed as a string. We could now jumble all of this in bad ways. We could, for example, get the order wrong. Okay, or we could replace the empty operator that's following the x by something else to make the effect of coalesce visible. or we could separate the individual components, the individual operand operator pairs by some other symbol. All of this is possible, and all of this would make sense in particular situations to process string output using SQL. Okay, so much for set generating functions, or table generating function, which maybe is even the better name, because what comes out of such a function is a table-like thing that we can iterate over. Okay, so these functions are going to stay with us. They are super useful, and we will discuss some of their properties and some of their uses in the upcoming videos. See you in a few minutes if you stay tuned. Bye bye.